and then kind of the results. The way I've structured the presentations, I'm going to go through our system first, and then the settings we use and the results we got from those settings. So it's up to you whether we're going to start the discussion during the settings part or during the results part. Okay, so to start, this is a small diagram of our system, specifically focusing on the web-based UI and rendering. So we have a few key processes, the browser process, the GPU process, and a few renderer processes. Every render process represents like a frame or a tab, so visible element. So we have a few render processes. Some of them could be in the foreground, like a foreground tab, and they can be in the background. Within those processes, we have a few threads that are important for compositing and drawing things, so UI threads, and they're also used for input. So just going through an example of like an input path through our system. So the EEVDF, so once the input comes in once we get the interrupt, the EEVDF thread wakes up, and then it will send the input to the main thread here to figure out where this input should go, which renderer needs the input. It will send it to an IO thread that does the RPC to the right renderer. From there, it moves to a compositor thread. Now, this thread here can choose to handle the input itself, like if we're doing scrolling, for example. So it knows how to handle that input by itself without going to the main thread. The main thread is where the JavaScript and all the web application will run. So if it doesn't know how to process the input itself, it'll go to the main thread. That's where the JavaScript handles the input. Once it's ready to display the UI, it's going to send it back to the compositor thread. From there, it will move to the GPU thread, and we have kind of similar processes. Sometimes it will need to go to the main thread, but mostly it'll go to the compositor thread, which will send it to the GPU. Now, the key things from this slide is that there are a few very important UI-based threads, and any delay in those threads will cause a delay in either the UI, so like drop frames, or it will cause a delay in handling the input. The other thing is we do have a few like normal threads that might handle video encode decode, for example, and we do have background threads in these processes, so they're not all equal. So some of the settings we're using right now, the UI threads are using -8 for nice, and any delay in the UI threads can cause, just like I mentioned already, but like drop frames or input. We do prefer, of course, running UI threads over background threads, but we do prefer running UI threads over even normal threads. In like a video conferencing scenario, if you want to type, we don't want to have a lag in the typing latency, but we can tolerate some video drop frames, for example. So your video quality might decrease as long as your typing speed stays the same. From what we've noticed, that seems to be the preferred way for most of our users. Okay, so the next step is how we structure the C groups for these processes. So here's kind of like the root top level. We have here a UI C group, which is 1024 CPU shares. And then the system processes live here. So the browser process and the GPU process. And then on the other side, the renderers are under this Chrome renderers. And then they're split into foreground and background. So foreground is 1024 and background is 10. So we want to limit how much CPU the background tabs get when there are foreground tabs. And then in here, you can have multiple renderers, and you could have multiple renderers in the background at the same time. We are looking at flattening this, at the very least, getting rid of this, and then pushing the foreground and the background up. And then also potentially looking at, just having a completely flat hierarchy and getting rid of this level. but we definitely need to keep the background C group to limit the shares. But that's still something we're looking at doing. But this C group structure, we'll come back to it a little bit later in the presentation. Just to give you an idea of the target hardware we're looking to improve here. So an example, this is just an example, like this is not the only hardware we're using. So we have EDU uses a lot of like the two-core Celeron processors. In general, when there are more cores for even like on ARM big little systems, our system ends up performing a little bit better. When there's fewer cores, like on this example, cores, that's where we get a lot of bottlenecks. Okay, so I'm going to kind of go through the settings we are using with EEVDF, or these are the settings that seem to show improvements for our case, and I believe they're all SCED features or in the debug FS. So the first thing is the default base slice for a two-core system, at least based on an early version of 6.6 EEVDF, would end up being 1.5 milliseconds. That showed for a lot of our use cases a pretty big regression compared to CFS. So we ended up going with 6 milliseconds, and that's mostly based on our testing. But 3 milliseconds showed a similar performance gains, and we'll talk about that once we show some of the charts. The other thing, which you might have seen some of the discussions on LKML, was we disabled eligibility. So this was based on testing and some thought process we had, and the idea is we want to limit the preemption of UI threads, especially by background threads. So a UI thread might not be considered eligible, but if there's a UI thread and a background thread, we definitely want to keep the UI thread on the CPU. And then with the nice values and the way the nice values adjust the deadline, we found that in general, the general fairness is still maintained, especially if they're both CPU bound. And then during testing, we found that eligibility on, in our case, adds a lot of context switching. So I'll show a chart to kind of point the numbers, what a lot means here.
There are two places where we evaluate eligibility. One is during the scheduler tick, when we do the picnic stars to see whether a task is eligible or not. Other is when a task wakes up to see whether the currently running task is still eligible. So which part is hurting? Is it even in the picnic stars, do you really want to eliminate eligibility? Because we have seen on server workloads that wake up preemption is a major problem, not necessarily the other part.
So when you say pick next task, do you have a specific case in mind? So wake up is where most of it happens. Where most of the time we end up getting kicked out too early because of eligibility.
Thanks.
Yeah. I think I went too far. Oh, go ahead.
Yeah, I'm surprised. I was expecting that you will enable eligibility to let your UI thread that wake up to preempt the current one.
Okay, so that's a very good point, and I forgot to mention that earlier. The UI threads are low latency, but they also run for a long time. So, for example, the main thread that's running the JavaScript, it needs to process the input and display the frame, and it will run for a long time. If we go back, maybe I can go back real quick. So if we go back to this compositor thread over here, this needs a lot of CPU time because it's handling frames from all the different renderers. So that's why, like during your presentation, I mentioned we actually might want to consider something where we can specify a low deadline, but also a higher runtime, a long slice.
Yeah, but just you don't care about your UI thread to preempt that wake up the current? You might wait a bit, but you won't then go as long for a long time.
Yeah, so the other thing here is like the nice value is set. So the deadline for these threads are lower than all the other threads.
Okay.
So when we end up picking the deadline, it will be pretty short compared to the other threads.
Okay.
So we were relying on that as opposed to eligibility to get onto the CPU faster.
So you use the nice priority to shorten your deadline and preempt the current one. That's the way.
Yes,
Okay.
yes. Okay. So the next is we removed no place lag here. And it kind of followed the same logic, or we used no place lag. So we removed lag-based placement. We followed the same logic where we didn't want to penalize important threads because our important threads are latency sensitive and long running. So it is very likely that they will accumulate a lot of lag, and then when they're moved based on when they're placed somewhere else, their lag will prevent them from running onto the CPU quickly. And again, it made it a lot easier to think about it with nice values and deadline. So you kind of can reason that we want to have our scheduling be based mostly on the deadline value. We removed no place deadline initial, or we added no place deadline initial. So this will reduce the deadline and runtime by half when the task is first placed on the run queue. So we felt it's kind of unneeded for all the tasks. And again, sometimes especially when the CPU is overloaded, a lot of the high priority tasks just stay on the run queue and they don't have enough time to go to sleep. So this will, if a background thread first wakes up and is added to the run queue, it's going to have its deadline and get it to run sooner, which in this case, we might not want it to do that. And then the last one is no run to parity. So no run to parity will keep the task on the current task on the run queue until it becomes ineligible. But when we disable eligibility, it's always eligible. So it kind of defeats the purpose of it. And then we usually, if there is a task with a lower deadline, for the most part, we want it to preempt the current task. So before I jump into the results, anyone have any questions here? Okay. Okay, so these were like one-off tests, or not one-off tests, like this is local tests that we did before we kind of tried to push it to more tests. I'll explain this a little bit. So the blue line here is EEVDF, so there's no the second E, so this means eligibility is off. The 3 milliseconds is the base slice. The yellow line is regular EEVDF with eligibility turned on and all the other settings. So this means all our, like EVDF has all our settings. EEVDF doesn't have any of our settings, so just stock eligibility or stock EEVDF. And then this is 6 milliseconds slice. Again, 6 milliseconds with our settings, and the red line is CFS. So this is key press latency in the meets and docks scenario. So we see like CFS and regular eligibility or regular EEVDF, even with 6 milliseconds base slice, end up forming about the same, and they have a latency that kind of ranges from a little over 250 milliseconds that can go all the way up to 500 milliseconds. But with turning eligibility off and all the other settings that we had, both 3 milliseconds and 6 milliseconds, the key press latency goes down, and it's a lot more compact. So there isn't as much variability, and it goes down from like around 250 to around 150. So it's a significant drop in the meets and docks scenario here. Same thing with the percent drop frames. So CFS and regular EEVDF stays up at around 15 to 18 with a wider range of difference. With EVDF, so eligibility and some of the other settings, both 3 milliseconds and 6 milliseconds kind of stay around the 10% range. So far it looked good. Digging in a little bit here. So this is the key pressed latency value. So this is an average of a few runs. So with the 1.5 millisecond, which was the default for our hardware, it had almost like 1 million switches. Average latency was pretty good with around 1 millisecond, 1.13 milliseconds. And then max latency was 400 milliseconds. Going up to 6 milliseconds base slice. So the key press latency went down to 178 milliseconds compared to 226. Which this was more closer to the CFS average. So this was a regression from CFS. CFS was close to this range here. The switches is still pretty high, so almost 900,000 switches. And so latency numbers are pretty similar. Max latency actually goes down, which is interesting. And then with eligibility off and all of our other settings in 6 milliseconds base slice, the key press latency goes compared to the 1.5 milliseconds, it's 50% almost. And then the switches goes way down. Maybe that's a 7. So it's like 134,000. Now the average latency does go up because eligibility is off. So you will stay on the CPU longer. The current won't be preempted as much. But interestingly, the max is kind of somewhere in the middle. Now, to test this a little bit more thoroughly, and to put it in some of our automated testing, we had to backport it from 6.6. So all the previous numbers was early 6.6 versions. Most of our boards that we cared about at that time were still on 5.15. So we had to backport EEVDF to 5.15. We backported an early 6.6 version, but we cherry picked a bunch of fixes to fix some crashes and other fixes that came in. We might have missed something, but at that time that's what we did. Running it in a wider test fleet here, most scenarios didn't show a regression or a performance gains, but there were a few tests that showed a perf gain. So the desks test here uses multiple desktops and it switches between them. So there's a lot of tabs open on a different desktops and it will keep switching between them. And this is percent drop frames specifically. The blue line is the regular CFS and the red line is EEVDF with our settings. So no eligibility. We couldn't, it was a lot harder to compare all three where you have vanilla EEVDF and EEVDF with our settings. So right now we just compared CFS and EEVDF. So with our settings, EEVDF showed again in this workload scenario a drop from about 15% drop frames to 10% drop frames, which is pretty good. Meets and docs we talked about, but that showed kind of consistent improvement across a lot more builds and tests. Kind of key press latency showed the similar improvement here. So it's dropping from like close to the 200 range to a much flatter line at around 100 millisecond range. Again, blue is CFS and then red is EEVDF with our settings.
Yeah, that was the question with your setting. So here you're writing EE, so double E, and that's your setting. And in the prior slide,
yeah, so
1E was your setting. Is that correct?
Yes.
Okay.
Because I was showing like regular EEVDF and ours.
Just to be sure.
I probably should have stayed consistent. So this is a mishap on mine.
Your optimized EEVDF.
This is our settings, right? So moving on to the next slide. So we wanted to send it to test this out on the field. So it would be hard to test all three scenarios. We were backporting to 5.15 in the field. We also wanted to minimize impact on users. So we only tested our settings with 5.15 since that's what showed improvements in the tests. As more boards start moving to 6.6, we actually it will be a lot easier to test regular EEVDF and then EEVDF with other settings, whether it's our settings or anything else that we end up testing with. But then we won't really compare with CFF, which doesn't really matter since the board is going to be moving to 6.6 anyways. I think I covered everything here. So all the charts from now on are field results comparing CFS and EEVDF with our settings. So there is no vanilla EEVDF for most of the chart, or all charts moving forward. To be able to run this in the field, we needed a way to be able to switch between CFS and EEVDF during runtime. Typically, this would happen once at login, and it will be sticky till the next reboot. So we weren't going back and forth a lot, so performance wasn't a major concern. So what we did was we added a procfs schedule EEVDF setting. When you wrote to this file, it would run a stop machine. Inside the stop machine, we'll dequeue all the tasks from all run queues. We will toggle a switch, and then we'll requeue them all back onto the run queues. The reason we did that is we wanted to make sure the V runtimes and the deadlines that were being calculated between the two versions were all consistent. I did notice that if we didn't do that, sometimes the task V runtime would be wildly different. The impact, like when it gets to the CPU, a lot. So again, performance wasn't a major concern here, but we wanted everything to be consistent. All right. So moving on to the results, we'll start with the good. So these results don't measure specific scenarios, right? So we just have metrics and how they improve across the field. We don't know what the user was doing. So we start with mouse pressed in the UI. So we see improvements across the board, almost with the exception of the 50th percentile, but the high percentiles, we see a lot of improvement. So in the 99th percentile, we see a general drop by 11.5%, 95 percentile, 8.64% drop in mouse press latency, and the 75 percentile, a drop in 5%. The 50th percentile went up by 1.4%. We see that trend a lot of times when things start moving from the higher percentiles towards the lower percentiles. So sometimes the lower percentiles will go up a little bit as the higher percentiles drop. And I'll show some other charts that depict this a little bit differently. Same thing in key press, but in the 99. Let me go this way. In the 99 percentile, it was close to 15%. Okay, so this is showing the mouse pressed in slightly different ways. So the 0 line here is CFS, which is the control, and then the red line is EEVDF, and this shows how EEVDF changed compared to CFS. Down here kind of shows the actual latency. So we see that a lot of latencies in the higher end, especially all the wild kind of 500 ranges, 200, 300 millisecond ranges, that all dropped, and then the middle cusp ended up growing. So a lot more. So basically, things from this side got pushed towards lower latencies. We do see also a drop here in the lower latencies, and it seems like they're pushing a little bit lower sometimes and a little bit higher sometimes. But this range is pretty low, like maybe 40 milliseconds or so, which generally isn't user noticeable. But this is the range where we're talking about 100 milliseconds, and it's very user noticeable. Yeah.
Yes. Very stupid question. I apologize. On the previous slide, I don't understand this plot. Percentiles, 99 percentile. I expect the 95 percentile to be larger than the 99 percentile, just by definition of percentile. So if you can.
Yeah. So the percentile. So this is the latency. So it's 400 millisecond latency. So 99 percentile is higher, but this is the percent change.
Okay.
Sorry, I didn't call that out. Sorry, yeah.
There is no occurrence that you have the time in the wire. All right.
Yeah.
Thank
So yeah, the 99 percentile is around the 400 millisecond range. So we saw a bigger drop there than the other ranges.
I just wanted to add, go next slide, or whatever. What this to me, to make it for layman's terms, or because I was a little confused by what this showed too, was basically basically tail latencies. So basically things that used to take a long time don't take a long time. This just means that the system's much more consistent, which means everything from low end just ended up in a single spot. That's why you see the big spike in the middle. It just shows a better consistency and everything. Just
also short latency seems to be less because it's like you have a higher
but the short
and long latency. Yeah.
And like we said, this is all coming from something we don't know what the user's doing. We're just basically so there could be some workloads that this could be a little bit less on, but just everything seems to be much more consistent.
Yeah, Youssef, one thing about when you mentioned switching between CFS and EEVDF, what about implementing these like a different scheduling classes? Like, do you think having the tuning knob would affect somehow the results, or?
So I don't think the knob would affect here because it's only done once after boot on first login. So it's not done throughout this. So it's after on first login, and then after that it sticks until the next reboot.
Okay, yeah, makes sense.
Oh, more questions? So again, touch pressed showed the similar thing, 17%, almost 99 percentile, 50 percentile went up again, which we saw similar behavior. This is the chart for touch as well. So again, the similar spike around the middle, more, wider drop across here. Again, we did see this, trend towards higher. But again, I don't expect this to start falling into the user noticeable delays. But it's just something to keep in mind that even the lower percentiles kind of went up towards the middle. So more consistent, as Stephen pointed out. Thread congestion here is how backlogged are our threads in the browser process specifically. And this showed improvement across the board, but the higher percentile showed a lot of improvement. So almost 26% improvement in the higher percentile, in 95 percentile, 10% in 99. It's represented as janks. So how often the user is likely to see janks. So that's good here. Tab switch duration, how long it takes us to switch between foreground tabs. That only showed improvement. So a lot of the higher milliseconds just went away and it got pushed towards the lower milliseconds. So nothing on this side here. This is page load render time. So when the page starts loading, how long it takes it to display on this side the first content, and on this side the largest content. So again, the higher percentile showed some improvement here. So 5% in the 99 percentile and 2.6% in the 95. This is largest content again about 5% and close to 3.8%. And actually, this showed up for improvement across the whole board here. This actually saves quite a bit. So this can save almost a whole second on how long it takes the page to load here. Okay, so the not so good results. So gesture scrolling here goes back to what I was saying, where the compositor thread can handle the scrolling itself and not send it to the main thread. This is the case here. So the input, so the scrolling goes from the browser all the way to the render. The compositor thread handles it itself. And then the result of that scroll is drawn through the GPU process onto the screen. Interestingly, we didn't see any performance gains here. We saw actually performance hit. So 99 percentile went up by 2.6%, and the 75 percentile went up by 2%. The rest were kind of negligible, but still leaning towards higher than lower. Again, the touch scroll percent drop frames, so same gesture, but mentioning the drop frames. Again, just a push towards higher or more drop frames. So more drop on the lower end and higher on the bigger end. The percentages are not huge compared to the win, but we didn't expect this since we saw all the other wins. So this is very interesting, and maybe a lot of discussion we can have here to kind of reason why this might be happening with the settings we're choosing. So we noticed most of the regressions that we saw, if there was any at all, were limited to this compositor thread. The main thread was not affected almost at all. Sometimes there'll be a very slight lean towards a regression. But generally the compositor thread was not affected at all. The main threads showed mixed results, right? So we did see a lot of those improvements, but there were maybe some slight regressions towards here, but it didn't even add up to 1%. So we didn't show those, but the compositor thread showed a lot more regression in the gesture scrolling. So thinking about this, one thought came to mind: does that thread have the right nice value? But I would not expect to see a regression since it has the same nice value in CFS. So why would EEVDF show a regression with the same nice value? The other thought is, can this be related to the C group structure? Since we have this added layer here compared to the UI, I wonder if there's a chance the C group structure can be causing a regression, since we have the double layer here. If anyone has any thoughts, we'd be happy to hear. I remember there was some comments on LKML about C group and EEVDF, but I don't know if this would play into here.
About the C groups, that I was thinking maybe the fact that I expect those in this scenario, the render track runs longer than when you put it on the GPU to render, maybe to do the rendering in.
So going back here,
yeah, in this case, the compositor there maybe it runs longer than in the previous case, and maybe the settings you choose might have.
I'm also wondering if we change the removing of eligibility to just wake up, I'm wondering if it's just a non-fairness thing, or could it possibly be, or?
Yeah, so answering Yuri's question first. So it shouldn't, if this runs longer, I expect it to show an improvement, unless this runs longer, causing the other threads in the stack to run shorter, but they're all here the same nice value. Sorry, can you repeat your?
So actually I'm saying is maybe because the other threads are actually causing the compositor not to run as long as it needed to run.
Right.
So I'm saying if other threads, I don't know if the eligibility could have been an issue, or the fact that we turn off eligibility for, because it's you said the compositor, this is a long running thread, right?
It is, but most of these are. So the main, the mains will be long, and these two will be very long. These ones will be likely short, but they're all the same nice right now.
Just to make sure that I fully understood, this is this platform that you control DVFS, because you haven't mentioned this at the beginning of this first slides. Do you change the frequency as well?
So the results are from the field, so it's across Intel and ARM. We didn't do anything special for frequency, so just whatever EEVDF is doing.
Yeah, so it would be nice if you can capture as well the frequency and compare to match the cycles.
We can do that in tests. We can't do that in the field. We can't match like the result, but I have to see if we can do that in the field. That might be a little difficult.
Yeah, remember, this is running in people's laptops out there. This is not a controlled setting at all.
Yeah, but you cannot trace that, or you can.
we have to be very careful what we trace. We also, like, it's very limited in what we could do, because it's running on someone's working on laptop, so.
We can think about it. I don't know. Yeah. But along those lines, we didn't see any power change. Early on in the experiment, it seemed like we were actually doing better in power, but it kind of trended towards just being even. So there's no power hit, at least. Comment, questions? Okay. So I just wanted to mention a couple of things that are currently being chatted about or in review. So there's the delay DQ approach, which will keep, I'm sure everyone knows it, but just briefly, it will keep the test still, even when it goes to sleep, it will keep it on the run queue, so to eliminate lag as it wakes up. So this is it's going to be similar to our no lag setting. Our no lag setting is just a lot more aggressive. We still haven't tried this. I believe Luis mentioned that this showed an improvement.
Yes, we did see initially improvements for Big Little in terms of performance, but later found out that it was actually making things migrate to bigger cores, which is why we saw the improvements. So that means that the energy regression as well.
Somehow
we're
it's
currently
wrecking EAS, and we still need to figure out why.
Sorry, Peter, can you repeat that?
So it seems to be messing up energy aware scheduling, and we're trying to figure out why exactly. But yeah, that's pending work.
Okay. So from our side, we still need to try it. It's a little harder because we're still on 5.15 for a lot of the boards. So as they move to 6.6, it'll be a lot easier to try. Sure.
Yeah, it would be even easier for you guys if you had locally reproducible use cases.
Yeah, it's hard to replicate that system in one process, but we'll keep thinking about it. And then again, the test results don't always match the field results. So in tests, we didn't see any regressions. In field, we did see a couple of regressions that I pointed out too.
Maybe try to replicate with a simpler synthetic benchmark.
Yeah.
Since you actually seems to have pretty knowledge about how the whole threads interact. Not sure if you already spent time or might be considering spending time trying to replicate that using RTAP. It's a synthetic thing, but if you kind of can design around your knowledge of the actual thing, not sure. Maybe
Okay.
that's easier to.
We actually we have someone, Hero, is working on a benchmark that is going to try to simulate some of the things we do without the full thing. Actually, I think he has it done.
So it's not a single process though.
Right.
He in our tests, we actually use the real docs and the real meat, but we do have a test where it uses like a video application and then a different notes application.
But the point of that was to make it so it'd be brought that other people could use it, like Peter or you guys could. That's should be done now. We should be posting that soon. So we have like a kind of a thing that, because meets doing these things are really, really complex. These tests are very, very involved and tries to emulate a real, it actually shows docs and running. So getting that to other people to test is almost impossible. So we had someone actually working full time on creating a test that would be kind of like to simulate it while we work on, but it could be given out for people to try. And that should be done by now.
Yeah. Okay. Any more questions or comments? So someone brought up skipping eligibility during wake up. We need to try this. I tried porting this to 5.15, but our tests would continuously time out, there would be no crashes. I haven't investigated it deeply yet to understand why this was happening. I suspect we might be keeping current on the run queue, or sorry, not on the run queue, the current running on the CPU a little bit more aggressively this way than what we originally had in 5.15. But I haven't investigated it fully yet. So as our boards move to 6.6 again, we're going to be able to try this as well. I tried latest 6.9 on one of our boards, but I ran into the same issue actually. The test would continuously fail because of timeouts, but no crashes. All right, other topics. This will be pretty quick. We talked about it during the presentation already. So a lot of our threads require low deadline, but do have a long runtime. So the current patch will only adjust either deadline through nice value, but the runtime stays the same, or it will adjust the runtime and then the deadline is calculated automatically. So if you adjust the runtime longer, the deadline ends up being a lot later. So there's no way to say I want a short deadline, but a long runtime. That might be a nice knob to have, but just throwing it out there. And that's it.
General questions. As far as I understand, we are using, there are a lot of knobs and flags and things you need to configure. I'm just wondering if you are missing opportunity to do a better job at maybe a simpler or more descriptive interface for, describing what the task needs.
Yeah, we were talking about that outside, me and Vincent, and internally, we're working on an API in user space to expose quality of service type scheduling to our users. We notice every subsystem tries to optimize on its own. And then we end up having mixed results in terms of what background means or what shares to use or what nice value to use, where most systems on Chrome OS just want a UI thread or a background thread. So we're working on a service, actually it should be implemented already now, to provide that quality of service API. So you request, you want your thread to run as UI, and then it will go ahead and adjust all these settings based on what we think is right. But at least it's consistent, right? So all foreground means the same thing, all background means the same thing. I don't know if we want some of that moved in the kernel, but it might be hard.
Is this library or daemon publicly available for others?
Yes, it's open source, yeah.
Because I know that, each people we are discussing about what should be the scheduler interface give you a different interface.
Yeah.
And it's quite difficult then to map that with what the scheduler can do. Typically, being a UI thread doesn't mean anything from a scheduler point of view.
Yeah.
It's mainly a matter of slice, deadline, whatsoever. So we need some kind of translation between what the user wants and what it should be, how we should map that to the scheduler in the scheduler property. And typically this kind of library are good, at least to test. You can easily test different nice priority slices.
Yes. Yeah, testing was one of the biggest selling points for this, because then it's localized, right? I don't have to go change all the different systems if I want to change what UI means or what program means.
And maybe we can expect then to have several different or system to go in to end up using the same interface. And once we'll have the same interface, then maybe you can consider this being the kernel interface. But right now, I'm afraid that if we came with your interface in the kernel, someone else would complain that it doesn't match his need.
Yeah, so
and the third one will have and so on.
So just real quick, Youssef, do you know if any of the conversation for LibQOS has been, or
We haven't started discussing anything upstream yet. We just finished implementing it and moving Chrome to use it, but we're still working.
yeah, so we should include OKML or something else, or sending the scheduler folks.
Okay.
Seeing this is what we came up with and that's now.
Last one, yeah. You mentioned this shim layer for what is an UI thread or what's the foreground or background. How is this? Is this the same as the Android folks using, or are you using something different?
No, it's different.
Why?
So we discussed it earlier, I believe, but I think Android wasn't as aggressive. I don't know. I don't remember now, but we did discuss it earlier. Do you remember that discussion? Okay. Yeah.
All right. Thank you.
Thanks.